This technical exchange is on the topic of case studies from UTC laboratories, upcoming UTCK laboratories, and UTCK labs implementing expanded capacity. And we have a busy schedule, as I mentioned. You can see it here, and it was, of course, posted on the website and on the invitation. We'll have 4 presentations from new UTCK labs that just recently joined UTC and Circular T. We will have presentations for more established labs that have joined the UTC a few years ago. And then 2 presentations from well-established developed labs in the UK and in India. So let me introduce the first speaker. I'll stop sharing. And our first speaker is Eleanor Trogli. She graduated and obtained a master's degree in physics at the Faculty of Science in Zagreb, Croatia. For more than 20 years, Eleanor worked in the private and public sectors on the establishment and maintenance of management systems according to the ISO 17025 standard in testing and calibration laboratories. She also worked as an assessor and was responsible for the assessment scheme of calibration laboratories in the national accreditation body of the Republic of Croatia. Eleanor has been employed at the Institute of Physics since 2020. Welcome, Eleanor. You're welcome to start your presentation and our technical exchange. Just a quick reminder, most of the presenters send their slides, presentations to Julia, so in case there are problems with network connectivity, Julia can help sharing the screen. Welcome, Eleanor.
Dear Marina, thank you for the introduction. Good afternoon. I would like to greet you all from on behalf of the Institute of Physics in Zagreb, and especially of my colleagues in the laboratory. I will present the establishment of UTC IFZG and process of joining UTC. And I'm going to start to present a laboratory for time and frequency as an organizational unit to show you context and the reasons for establishing the National Calibration Laboratory for Time and Frequency. And from the technical point of view, I will talk about facilities and environmental conditions, set up for UTC IFZG generation, data analysis, and our achievements and objectives for next period, and conclude with one suggestion or proposal. Time and Frequency Laboratory is part of the CALT department of Institute of Physics in Zagreb in Croatia, and department was established following the CALT project, which was recognized as strategic research infrastructure project of the Republic of Croatia and co-financed by the European Union. And total investments was about 16 million euros and included completely renovation and expansion of 1 of 3 institute buildings and its equipment with the state-of-the-art technology for the base laser, based on advanced laser techniques. Also, one goal was establishing the National Calibration Laboratory for Time and Frequency. Time and Frequency Laboratory is part of Quantum Technology Group in CALT department and is an experimental group working in the field of atomic physics, specifically cold atom, quantum metrology, and quantum, And in the field, in research in the field of quantum metrology, included development of an optical atomic clock based on cold strontium atoms trapped in periodic optical potentials. It will be the first and so far the only one in this part of Europe. And in addition, the National Calibration Laboratory for Time and Frequency was established to meet the need for timekeeping as basis. And also, Croatia doesn't have its own reference standard for time and frequency. In the Time and Frequency Laboratory, there are 3 employees. Time and Frequency Laboratory is located in CALT building, and you can see floor plan of the laboratory. Laboratory space consists of 2 rooms, completely detached and both air conditioned. One is used for equipment storage and measurements, and the other is used as working place. Following environmental conditions are provided for temperature, relative humidity, and electrical powering are provided, monitoring and controlled, and the laboratory is equipped with an independent UTC and connection to generator to ensure stable and constant power supply. This is a setup for UTC IFZG generation. It consists of one high-performance cesium clock, which provide reference signals of 10 MHz and 1 PPS. Also, 1 PPS signal from the back side of the clock gives a local time scale UTC IFZG. Laboratory is equipped with 2 high-performance cesium clocks, 1 standard performance cesium clock, 2 sets of GNSS receiver with choke ring antenna, and servers for data storage and managing and controlling devices in the lab, and other common equipment, common use in timekeeping. On the roof, there is a choke ring antenna with a clear view of the sky above 10 degrees, and all delays from antenna to receiver were determined. Also, receiver and antenna were calibrated in G1, G2 tour in May last year, organized by ROA. RINEX and CGGTTS files are automatically downloaded from the receiver to laboratory server, and next day in the morning, and uploaded to BIPM server, FTP server in the afternoon. We received an email notification about it, and it is all done by Python scripts, thanks to our colleague Domagoj Kovačić. Also, clock and meteo files are every day also automatically uploaded to BIPM FTP server next day, also by Python script. And by Python script, it is provided a common view comparison of time scales with other NMIs, and from which we can calculate our frequency, drift, and offsets. Laboratory also use stable 32, origin, influx database, and Excel. I can summarize laboratory establishment and achievements in one timeline. The laboratory was equipped through public procurement through project co-financed by European Union, and in 2000 and delivery started in 2022, at the end of 2022. That year, laboratory also attended Euramed CCTF meeting for the first time. And in 2023, in March, laboratory started with establishment of calibration methods for frequency and time interval. We sent the second high-performance cesium clock and time and frequency counter, oscilloscope, and equipment for time and humidity measurements to an external calibration to meet traceability for establishment calibration methods. Also, that year, the laboratory get approval for participation in UTC from the State Office for Metrology of Croatia, and also receiver and antenna were calibrated in May in G1, G2. Laboratory started uploading files to BIPM FTP7 in November 2023, and laboratory also established a management system according to ISO 17255 standard, and in December applied for accreditation. And last week we became participant in UTC and Rapid UTC. So you can see, I'm happy to show you our first results in Circular T and Rapid UTC reports. I will end with objectives of laboratory for the next period. And there are reporting of second clock to BIPM, becoming a DI for time and frequency in Croatia, recognize the needs of the economy and society, and place the laboratory in the correct role of DI in Croatia. And I will conclude, if I may, with one suggestion for improvement to the BIPM website to help new UTC participants, to issue a procedure with the key steps at one place, which will include an example of the simple set for UTC, local UTC generation, with a diagram and explanation of all components and initial configuration of receiver, determination of antenna coordinates and delays. I will stop here and say thank you for the invitation and attention, and especially thanks to BIPM and Euramed.
Thank you very much, Elinor, and congratulations. You're really
Thank
brave
you.
participant in Circular T. This is excellent news. We have maybe time for one question. If somebody wants to ask, please raise your hand.
Yes, please.
I don't see anyone raising their. Oh, I see Giulio has a question.
Yes, please.
Yes, I saw from your slide that you have also a ComNav receiver, GNSS receiver. Is this a timing receiver or?
Yes, it is timing receiver. Maybe it is a septentrial timing receiver, yes.
Ah, okay, because in the slide was indicated two receiver, one
yes, two
ComNav.
receiver, two for time transfer, time keeping receiver for and two choke ring antennas. But we use for still for our UTC participation only one set.
Okay. And can you comment on this other brand? What is your experience? If
I haven't so much experience about other receivers. I'm sorry, but I think that this one is good.
Okay, thank you.
Thank you.
I would like to thank Elinor again, and thank you for your suggestion. I think this is exactly very helpful at what we're looking for. what training materials to provide to UTC labs and on the BAPM website. And I'm sure that this is what we will be working towards in the working group TI together with BAPM and the working group in education and education capacity building and knowledge sharing. Thank you again. Our next speaker is Bohobyon Nishonov. He is the first category specialist at the Time and Frequency Laboratory of the Uzbek National Institute of Metrology. Mr. Bohobyon has 6 years of experience in the field, and his background is related to metrology and certification. Bohobyon is also doing his PhD in the field of measurements. Welcome, Bohobyon. Please go ahead with your presentation.
Thank you very much. How about my presentation is visible? Okay, thank you. Good afternoon, everyone. I am Bohobyon Nishonov, first category specialist of Uzbek National Metrology Institute. Today with me, Lyubov Borisovna, our leading specialist in the Time and Frequency Laboratory. Today I'm going to present on the behalf of Uzbek National Metrology Institute about the new UTC UZ lab and its experience. Firstly, I am going to indicate creation of time and frequency standard. First step, we began development of a terms of reference project based on industrial needs, obtaining the recommendation of foreign experts and signing the contract based on the requirements of the law on public procurement. Second step is in the process still personal training in the foreign national metrology institutes. And third step, delivering the time and frequency standard to the laboratory installation, configuration, and so on. And running the time and frequency standard in the test mode and experimental work on the generation of UTC UZ. And first step is also in the process still, personal training in the Uzbek National Metrology Institute by the international experts. And next step is preparing an application to the International Bureau of Weights and Measures for the being a member of International Atomic TAI Club. It's performed successfully. We are very thanks for this. And also next step in the process still, participation in the K comparison, carrying out measurements with the designated laboratories, and implementation of KCDB CMC based on positive results. Firstly, we developed the legal basis of creation of time and frequency standard in Uzbekistan. We also began the works in 2017 based on decree of president. It considers the creation of time and frequency standard with GLONASS and GPS signal receivers and purchasing the highest precision measuring devices. And in 2019, also decree of the cabinet ministries of the Republic of Uzbekistan considers establishing a time and frequency service that performs national time scale in Uzbekistan. And also final presidential degree, it also time and frequency standard is included in the list of standards which are purchased based on state budget of the Republic of Uzbekistan. And finally, we made a contract with the National Metrology Institute of Turkey for the creation of time and frequency standard in Uzbekistan. In the next step, of course, personal training. There is our personals. We are 3 in the laboratory. Sharoz Ismatullah, head of department, has got 10 years of experience. And Lyubov Borisovna, also leading specialist, has got 36 years experience in the field, and me. We training organized in the six step, three divided by 2 steps. Fourth one in the Foreign National Meteorology Institute, and next one in the our own laboratory. It is somehow about the training process. In the next step, we began the projecting and planning lab infrastructure. Our laboratory is located in the first floor of our institute, and the top of the second floor, I mean roof of the second floor, our antennas is located. From here, you can see it is about the infrastructure of our laboratory. We are also trying to provide all requirements, based on temperature and electricity, other security requirements by using this kind of infrastructure in our laboratory. Here I can say that until creation of time and frequency laboratory based on cesium clock, we also had a laboratory, time and frequency laboratory, and it is our new view of our time and frequency laboratory. It is our calibration and measurement capabilities. Nowadays, we are performing frequency measurement based on phase comparison, frequency stability calibration, and time interval, pulse width, and rise fall time measurements. It is a block diagram of our time and frequency laboratory. We have also 2 cesium clock and offset generator, pulse distribute amplifier, and frequency distribution amplifier, and NTP server. We have with antennas and GNSS antenna and TS5 receiver, and other device for the calibration and performing the measurements like signal generator, counter, and pulse generator, so on. We have launched our time and frequency standard last year on November with our friends from Turkey National Meteorology Institute. It is some photos of this event. And membership of BIPM TAI Club and comparison. Joining BIPM TAI Club, in order to become a member of TAI Club, Uznem director applied the request for the joining. And also we have become a member of time and frequency standard, and we are glad which there is indicated Uzbekistan in the also map. And nowadays we are also participating in the key comparison, which is organized by the TAI Club, and also we are also participating in the pilot comparison with the National Meteorology Institute of Turkey based on the comparison of UTC UME and UTC US time scales. It is about we created special website for the users about the accurate time in Uzbekistan, which is linked our time and frequency standard. If I told about our future plans, firstly, we are going to calibrate our receiver under G1 or G2 laboratories. Now our receiver calibrated by the manufacturer. And second one, we are planning providing peer review of time and frequency laboratory under the COMET based on requirements of the ISO 17025. And we are going to participate in key and supplementary comparisons, and based on positive results, we are going to publish our CMCs in the KCDB database. And we are also going to implement time and frequency service in Uzbekistan. Nowadays, we are developing the presidential degree, which is now under expertise. Soon we will announce, and among Uzbekistan will be implemented time and frequency service. And also, we are going to develop our calibration system capability for frequency generation measurement up to 50 gigahertz, including signal analysis and phase noise measurements. This year, it is 100 year of metrology in Uzbekistan. We are going to invite all of you for the anniversary of metrology activity in Uzbekistan. From these two pictures, you can see in 1924 year, it is the first measurements in Uzbekistan, which is legal, I mean. And from this point, we have begun metrological activities in Uzbekistan. Thank you very much. So.
Thank you very much, Bjorn, for your presentation, and congratulations on 100 years of legal metrology in Uzbekistan. This is excellent. We have time for one question. Please raise your hand if you have a question. I don't see any hands up. I want to remind everyone that the presentations will be available on the BIPM website for looking at them afterwards. And if you have questions, you can contact the speakers or you can post your questions on the Working Group TAI forum, which is also, you can find it on the BIPM website after you sign in. With that, we thank Bjorn again, and the next speaker is Jürgen Appel. Jürgen has an academic background in experimental quantum optics, and he is a senior researcher in the quantum metrology team at DFM, the Danish National Metrology Institute. He has the technical responsibility for DFM's time and frequency activities and has set up and is operating the UTC DFM. Welcome, Jürgen. Please share your screen.
Is that button gone? View, signs, recording.
The share screen button at the bottom, the green square.
Yeah, there it is, gone. Good. Hi, I hope you can see my slides now.
No, you're not sharing. You need to click the share button.
Oh, it shows one here. Sorry, it doesn't. Share screen, screen one, share. And
we can see a screen
there we
now.
go.
And presentation. Excellent. Thank you.
You can see my screen. Good. Okay. Thank you very much for giving me the opportunity about talking about UTC DFM. Denmark doesn't have a very big national metrology institute. In fact, the landscape is split up between 7 so-called Gulken technical service, approved technical service institutes that provide advanced technology services to Danish industry. And DFM is only one of them. And we have also we are the National Metrology Institute that Denmark is obliged to have since joining the Meter Convention in 1875. DFM is rather small. We only have 35 people around in total, and about 7 million euro turnover in last year. And we are a non-profit organization, 100% owned by the Danish Technical University. And that background, in 2021, we have been awarded with a grant for establishing a Danish national time reference as one of the last countries in Europe. And so we got money for about 2 researchers and some expenses for minor equipment. That is not a lot to get started with UTC. So therefore, our focus was on getting a low-cost, simple, low continuous support implementation of UTC, and this is what I'm going to present about, and I hope so that the Danish realization can serve as an inspiring for inspiring NMIs who want to set up a minimum UTC realization. So for a minimum UTC realization, what you need is a clock, a frequency pulse distribution amplifier. Obviously, you need some kind of a laboratory and some way to transfer your time to BIPM. So a calibrated GNSS receiver and antenna is the easiest option. And of course, you also need some operation infrastructure, some computers, power, climate control has been mentioned, some access to the antenna. The first question we had was, which clock do we want to buy? Our budget was limited, so to about 70,000 euros. And as we heard already in the first series of talks last week, the requirement is to keep time below 100 nanoseconds in a time drift below 100 nanoseconds a month. And that sets the performance limit to be better than 3.8 times 10 to the minus 14 in relative uncertainty. And so we did a survey of all the clocks that were available on the market where we could get prices from. And you can see an Allen deviation diagram here on the left side, where you see the active hydrogen masers in dark blue, passive hydrogen masers in light blue, cold rubidium atom clocks depicted in brown, and then there are cesium beam tubes, the high performance and normal performance in yellow, and some other oscillators that obviously don't work as atomic clocks for a UTC lab, but they are just plotted here in comparison. The ones that were available to us with our financial limits are the ones with the squares, and you can see that it basically boiled down to cesium clock like the 5071 or passive hydrogen masers. It would be very interesting also to hear about whether there are some labs running cold rubidium clocks in UTC now, but at that time they were not some of the commercially available ones as far as I know. And looking at this, then we had to make the decision between the two. And because of the much lower Allen deviance curve, we choose to go for a T4 science passive hydrogen maser. Also keeping in mind that that would also be a very nice reference for phase noise calibrations where the performance of the cesium clocks is not so good. So it looked like a much better all-round equipment at that time. So the T4 science passive hydrogen maser is very similar to the Russian-built Vremya VCH 1008. And since we bought our maser and got it delivered in March 2022, the company has been sold, and T4 Science has been owned first by Aurelia and now is part of the Safran Group, as far as I'm informed now. Yes, unfortunately, because of our tight budget limit, there was no room for multiple clocks and no resiliency or redundancy within our current grant. So what you will see is just a UTC realization based on a single maser. We, of course, hope this won't stay this way, and we're planning to build out at a later point in time. Let's talk about the features atomic clock should have. It's very nice to have a built-in battery, and this maser we have has a built-in battery support. We don't know exactly how long it lasts. It's supposed to be longer than an hour, and this really makes working on your rack, especially if you work on your uninterruptible power supply, much more relaxed when you know that if everything goes on, the maser will continue running. So dual supply options, having a DC and an AC supply, is also a very nice feature to have if you have a clock. We choose to have our uninterruptible power supply to run on DC because more efficient, but if we want to, we can still plug in a wall plug and power our maser that way. Multiple frequency, 10 megahertz and 1 PPS outputs. It's better to have multiple than one. I know at least for one other NMI where one of the outputs broke, and if that happens when you have only one clock, it's nice to have a second output that you can calibrate it beforehand, that you know that you can switch over. We already heard last week in the talk from NIST that if you have digital tuning of your clock available, this eliminates the need for a microstepper. And so it's very nice to have that. And it's also one of the features of our Mesa. So we can tune the frequency at outputs and steps or units of 10 to the minus 15, which is precise enough that we don't see the quantization noise in our daily measurements. It's also nice to have a readout of the internal log parameters. We log every data we can, just in case, and to see whether everything goes wrong or if behavior changes. You have to remember, if you set up a UTC lab, that the timescales on which things go wrong until you discover something goes wrong, if it's not something drastic, are very, very long. It can take a month until you realize that something is not working exactly like it should. So logging data is really important, and also documentation of the communication protocol. We are hoping for very long maintenance intervals. The high performance cesium clocks need a change of the tube, rather short intervals. For the Mesa, it should be longer. So until now, we can't see any change of the hydrogen pressure. So we'll see what happens. And as I said, a low phase noise is nice for frequency measurements, although not essential. If you run a clock, if you have a cleanup oscillator, that should also work. And the digital frequency tuning, already mentioned that. What you don't really need, but which many clock sellers want to sell you, is that it has a built-in GPS or GNSS receiver. You can't really have that. The clock should run freely and shouldn't be locked to anything else. Remote management and internet access, I would also advise against that. That's just things that can go wrong. The last thing you want is that the firmware in your instrument crashes or that someone else meddles with your clocks. So that's features that many clocks might have, but at least I can't see any point on having those in a clock laboratory. Also the communication protocol, if that requires a Windows machine or so running, that makes things really difficult. If the power goes out and you want to know whether your Mesa is still running nicely, if you need special software to control it, that means that you also have to have the whole equipment running on a UPS. If you don't need that, you are much better off. Also in the laboratory, we have experienced that USB connections never really work over a long time. Sooner or later, something hangs up and needs to be reconnected or restarted, and restarting your only clock is certainly not a really good idea, as you can imagine. The last point, resellers and distributors. I already mentioned that the company that our Mesa has produced has been resold and shifted owner a few times. So far, this has not been a problem with our Mesa, with our weather station. However, we had some issues that we didn't buy directly from a distributor. And so if you have a very complicated chain of supply, that makes it really hard to get in touch with engineers that need to tell you all the details, and you will probably be one of the customers that is most interested in all the intricate details of the device you buy. So if you can get a direct handle on the people who built the things, that's a big advantage. So let's come to how our equipment looks like. This is pretty much the whole setup. So it all fits so far into one single rack. We have a second rack available for time distribution, but we haven't come to that point yet. The core of the setup is the Mesa located there. Then we have a frequency and pulse distribution amplifier located there. We need a GNSS receiver. We went for Septentrio based on the experiences of our university colleagues and the colleagues who run the geodesic stations in Denmark. So please note, this is all just examples of equipment. I can't really endorse those before others because I haven't tried others, but those seem to work quite nicely for us. UPS, we have a pack of 4 batteries down there, and industrial type DC power supply running there that gives us uninterrupted power for over 9 hours. And this should be enough to, if push comes to shove, to start up a gasoline generator. The whole thing has its own private internet to be sure that no one else meddles with the devices. A Raspberry Pi running on the UPS as well, so that monitoring also works in case of a power breakout. We have a Modbus logger for logging all the environmental data. So, and there we have several environmental sensors from Lamprecht and Vaisala. It's on the roof and in the laboratories. Last but not least, there's a small Linux NTP server serving our time currently. And of course, we want to, in the future, extend that to some White Rabbit time distribution. But so far, we haven't gotten to that yet. The GNSS installation, a really nice feature, which I really can recommend to everyone, is to make a big pipe. Yeah, you can see in the background, there's a 100mm pipe that goes all the way up to the roof. And that makes it really easy, for example, when you have the calibration of the traveling receiver to install that, just throw the cable through and you can install the antenna. And the antenna, it's nicely mounted on some metal T-clamp type rails, and that makes a stable mount, which is important because the positioning of these antennas can be traced down to a few millimeters. I think the position has changed over, I think, 2.5 centimeters during the last year. And that might as well, the building being changing, or and not just the uncertainty of the positioning. Also, we contacted our G1 Institute from Euromed. That's the Royal Observatory of Armada is one of those, and they were very helpful. And only within a few months after the contact, they sent us a traveling receiver for calibration. And in that respect, it's also important to keep the cable length below 30 meters or so, at least, depending on what your G1 Institute's traveling receiver has coming with it. The second part is that we were worried about EMP damage from thunderstorms. We only have one setup, and if that goes bad, that would have disastrous consequences. So we had some surge protectors there, and we also wanted a second GNSS output, and so have an active GNSS splitter in our setup. This, of course, makes cable delay calibration more difficult. We heard about the different procedures for the calibration also last week, and the step reflection method that was mentioned doesn't work well with these suppressors. They block everything below 800 megahertz, so the step signals do not go through. So you really have to calibrate them in single and add up to, and make sure that that you power your GNSS splitter, because otherwise, because it's an active device, there's also no signal coming through. So it's very nice to buy a cheap vector network analyzer for delay measurements at the GNSS frequencies, and getting a calibration kit that I can recommend to everyone. It gives a very nice method of measuring cable delays down to below 100 picosecond precision. The second part is, once you have everything installed, there's the 1 pulse per second coming into your pulse distribution amplifier. 1 pulse is coming out to the GNSS, and the next input, number 2, that's our UTC DFM reference point. And it's important that you also think about how this circuit diagram of that one looks like. So our frequency distribution amplifier has a 3.3 volt output with an impedance of 13 ohms. That's less than a typical 50, but the advantage is that it can drive TTL signals into 50 ohms, which is really nice. And on the other hand, that means it makes reflections if the load isn't 50 ohms. So on our GPS receiver, the input impedance is high impedance. So it's a really good idea to put an terminator there. If you don't do that, you get reflection signals, as you can see here on the bottom, and the traveling receiver didn't have that. So you have to really be careful that you don't trigger on the wrong edge. just always be aware what you put in and monitor with oscilloscope, and be sure what you're doing when you do don't follow just blind in the manuals.
Jürgen, sorry to interrupt you. We're running short on time.
Yep, I'm stopping there.
Okay.
The last thing is we need to steer the clock and keep the offset small. And so how does it go? So you can see the difference between UTC and UTC DFM here. First, we had just a model of modeling our clock that was just a constant drift in frequency, and that didn't work too well. Now we have a model using an exponentially a frequency that exponentially nears a final frequency that works much better. But you can see we don't keep our time offset as close to zero as we hope to. So this is a very tricky thing. So it takes really, really long time to get a good model. And even then, there are limits on what you can do. But on the other hand, if you meticulously report everything you do in the clock steering, and especially with the right signs, then even with just a single maser, you can get a nice clock and keep it running. And so we have been trying to do that, and now we carry 1.3% of the clock weight in UTC, and there are only 42 clocks that have a higher weight than our simple maser system. And so with that, I'd like to conclude, give my thanks especially to the people who helped me with the receiver calibration, and to the very warm welcome and support from BIPM in getting everything running. This is a team, and I'd like to thank you for your interest and your attention.
Thank you very much, Jürgen, for this presentation. It will be very useful, I think, for people to look afterwards at the details. We have to rush. So I'm inviting, there is no time for questions. I'm inviting the next speaker, please. So if, Jürgen, you stop sharing your screen. Juan Jose Mendoza is an electronic engineer with over 9 years of experience in metrology. He's currently supervising the electricity, temperature, and flow unit at the IB Metro, Bolivia. Active participant in SIM working groups and evaluator in the fields of humidity and flow, Juan Jose is in charge of Metro's time and frequency laboratory. Juan Jose, please share your screen.
You can see my screen?
Yes, we see your screen. Thank you.
No, it's okay?
Yes, it's just not in the presentation mode, but we can see it.
Okay. So let me check. No. Sorry. No, it's okay, but true.
Good.
You can see my screen. Hello.
Yes, I think Marina disappeared, but we can see your screen. You can start.
Okay. Thank you so much. Thank you for the opportunity in this meeting. The topic is process to join in UTC. First, I will present the background information to the laboratory. In 2012, we acquire and implement the symmetrical rubidium frequency standard No? We implement a common view, a GPS measurement system receiver. In 2013, participate in SIM time scale. No? SIM as common view as main receiver. No? From 2013 to 21, we dissemination service, the time service by NTP server and our web page. For IP synchronization, we have the IP address, and in 2023, we acquired the symmetrical NTP server S650 in order to improve the time dissemination. We are participating in a SIM time network and CNTP server comparison. We have the session clock standard with a time transfer receiver. This measurement has been donated by Metro by COICA. The first system has been donated by MIST. This system has been donated by project by COICA. We acquired an interruptible power with supply and an autonomy to 20 hours in case without energy possibilities. A new national law in 2019, a new national law about the official time for plurinational state from Bolivia was approved. Law 1256, law of October 24th. The purpose of this law is to disseminate and authorize the broadcast of the official time in Bolivia. This is the motivation about the participate in to contribute in UTC. After that, we configure and set up the laboratory by this configuration. We have 2 NTP servers for dissemination. We have 2 receivers, common view and NIST transfer server. Our session clock is a standard for UTC. That's just the setup laboratory. We have 2 connections, internet connections for redundancy, and in our NIST transfer receiver, we have 2 internet connections. This is the picture, our laboratory. Dissemination of time, we update our website, and we have implemented our web club. This is an example. This is the address, and we have disseminating the time in the screen, our ministry. So the process for contributing to UTC, the first step, we have the document. We review the rules and guidelines from BIPM webpage, and we send the letter application to participate in UTC and necessary forms by email. The TAI department sent us the configuration document with the necessary information to connect to the BIPM FTP server to upload our data files. We have the new type time transfer receiver, so the measures have to provide in CGTTS format. We have the system calibrated by NIST. We send the certificate calibration. The CCTF recommend to maintain the offset UTC minus UTCK within 100 nanoseconds. The process, we start with a test about 6 months for a computation of UTC. TAI department analyze our data file without official enter our clock in UTC. And after that, TAI department require the files clock, and this is the configuration for a clock measurement. And we use an application FTP protocol to upload the files required to the FTP to the server. And this is our file in CGTTS format. And we have the coordinates, we have the necessary delays for configuration, and this is the file, and this is the screen our receiver. After that, from May 2023, we are participated in contribution to UTC. This is the circular T. Now, this is our future plans. This is the traceability chart. No, this is the dissemination for time. This is the IP address with the time transfer receiver, NIST TAI, and this is our for sign time network. And the future plans is to implement new services such as this is chart traceability for to national industry. We have to develop new services. The future plans is we are working to develop a stopwatch calibration, but inductive method. We are thinking to implement the frequency counters calibration. The most important challenge for us is to maintain the contribution to the UTC through the technical support for our time and frequency system. Develop and implement the quality managed system for time and frequency toward international recognition, QSTF, and wrote to the laboratory time and frequency of the method to declare the best CMC calibration in the KCDB platform with the scope of the laboratory. That's all. Thank you for your attention.
Thank you very much, Juan Jose, for your presentation. If somebody has an urgent question, just one question, raise your hand. Okay, I don't see any questions. I want to thank, oh, we have a quick question from Wohobyon.
Yeah, just my questions about the CMC publication. Did you already begin any activities or comparison or not yet?
Not yet, not yet. We are planning to participate in that way.
Okay.
Thank you, Juan Jose, again. This ends the first part of our very busy agenda. So I invite, without any break, the next speaker from the group of labs that are extending their capacity. And the first speaker is Claudia Fernanda Rodriguez. She's an electronics engineer and project management specialist. She's been working at the Time and Frequency Laboratory of INM Columbia since February 2019. And Claudia Fernandez, she's been a winner of the 2021 SIM Early Career Metrologist Award. Claudia, please share your screen. And you also have 10 minutes.
Thank you, Marina. I share my screen. Maybe you can show.
We can see your screen. You can start. Thank you.
Thank you. And special greetings to all of you. I will present the development of the CNC program at the NMI of Colombia and the process to publish them. Firstly, I will talk about a generality of the calibration and measurement capabilities. The mutual recognition arrangement seeks to bring equivalence in all the measurements in the world. The only way to ensure that this happens is to normalize our way to measure and express the results. And the product of this process is the CNC. And every NMI that is part of the MRA and can provide enough evidence of the measurement skills in the time and frequency metrology can register the capabilities in the Appendix C of the KCDB in the BIP. We have to take into account the following highlights with the purpose of maintaining the vitality of the CNCs for your laboratory. The CNCs have only a vitality of 5 years. After that, you need to perform the same exercise to maintain your CNCs. The values can be updated for better or for worse. And this depends the actual situation in your laboratory. There may be changes in your equipment or environmental conditions or new calibration methods. To demonstrate the CNC vitality, you need to show records of your work in comparisons, publication of your work, such as journals, conference proceedings, and others, the participation in working groups, trainings, and continuous improvement through research and development. Well, now I'm going to present our experience on the publications of the CNCs. Firstly, we identify needs of the accredited laboratories and the industry, mainly in economic sectors like electric, communications, pharmaceuticals, transport, and others. Knowing these needs, we review our resources, especially the infrastructure, the training staff, and the economic resource. Perhaps these CMCs were focused on industries and accredited laboratories, therefore provide traceability in physical and chemical laboratories at the NMI. We identified that the main needs were focused in the calibrations of stopwatches, tachometers, frequency standards, and frequency generators and counters. This is the picture that shows the first setups use of the publication of our CNCs. You can see a Cesium atomic clock, frequency generators and counters, and a comparison system. These instruments supply the calibration needs. Most of them were donated by technical cooperation in this time. The team in charge of the time and frequency laboratory before 2022 were Liz Hernandez and Nelson Baumont, who developed all the CNC program. The NMI of Colombia was created in 2012. Next year, Colombia signed the MRI and begin the accreditation via NBLab. In 2014, the SIM Quality System Task Force approved the quality management system of the laboratory, and in the same year, the CNCs were submitted for evaluation by the RMO. These services was traceable across UTC NIST via CMT comparison. In 2015, the CNCs were published in the KCDB, and the first results of the data submitted to the International Comparison UTC was released in the Circular T in September of 2017. And then the laboratory had the first peer review and the NBLab accreditation finished. By the next year, the INM began to contribute in the International Time Scale UTC, and in 2022, we have the periodic peer review. Talking about the traceability scheme, we have two cesium atomic clocks and use your frequency signals as an input of the comparison systems. We have two comparison systems. One of them contribute to the UTC, and the other is a backup in the comparison of the SIM time network time scale. It's for ensure the measurement traceability to the international system of units. Well, what do you need for the declaration of your CNCs? Firstly, to be a signatory of the MRA as a member or an associate state, to fulfill the quality assessment under ISO 17025, a peer review in the service that you want to publish. Maybe it's better if the evaluator is from another NMI with a CNC recognized. You need a comparison like CCTF key comparisons, supplementary comparisons, or others. You can take into account the guidelines available on the CCTF webpage. What do you need for the approval of your CNC? you need to prepare your CNCs for submission to the RMO, and the approval of your quality system and the technical capabilities from the RMO, and the approval of your technical capabilities from all RMOs in the world. And some criteria for acceptance of CNCs are the uncertainty must be based on all contributions of type A and B following the guide of expression of the uncertainty measurement. The classification of the services in time and frequency, the traceability scheme, and the CNC Excel file following the CCTF guidelines. Well, the lessons learned were the following. CNC can be published via CMT traceability in the case of the SIM region via CMT, or directly via UTC or a list of comparison support. Backup standards are essential to ensure the reliability even during equipment failures. Listing the CNCs in the KCDB shows our capability and help to support local and regional needs. Publishing, participating in working groups and audits, maintain the laboratory's visibility, and regular reviews help track capabilities to ensure competence and identify improvements. Continuous learning in new measurement methods and technologies is vital. Well, and what is our future plans? Is improve the CNCs published using new equipment, acquire equipment to remain the services and for backup, establishing new CNCs and new services according to the new industrial needs, training and development in measure methods, common view and other techniques, and quantum technologies. And thank everyone for your time. And I hope this little explanation helps some laboratories in order to establish the CNCs.
Thank you very much, Claudia, for your presentation. It was an interesting example of a lab that started with CMCs and then became the UTCK lab. We have time for one very, very short question. Anyone wants to raise their hand? Okay, I don't see hands raised. Thank you very much again, Claudia. The next speaker is Laura Gassi. She has a PhD in spectroscopy and integrated optics, and Laura worked in the laser industry with pulse lasers and frequency combs for 7 years before switching in 2020 to the German Aerospace Center, DLR, where she now leads the timing systems group dealing with generating robust and precise timescales using atomic clocks for Galileo and other applications. Laura, welcome.
Thank you, Marina, very much for the introduction, for the invitation. Can you see my slides already?
Yes.
Okay, great. Okay, so quickly. So the motivation on why we decided to expand on our capabilities is simple. The funding of a new institute and establishment of new research lines. So just background for you. Our UTC DLR used to be generated in the Communication and Navigation Institute, called also KN. It's been going on for 20 years, and it used to be based on the cesium standards, on 5071A cesium standards. Johan Furner, who was in charge of the UTC DLR, left KN in 2019 and joined the newly funded Galileo Competence Centrum. so-called GK. And there he started the new the timing system in 2020 to continue working on UTC DLR. So we took that with him, but he also started the robust precise timing facility for Galileo that I will explain later. However, we don't have our own building, we don't have our own labs, so UTC, DLR, and the RPTF were hosted in a 20 square meter lab in Caen. Okay, quickly our UTC DLR scheme. It's fairly simple. It's based on an active hydrogen maser. We switched to that in 2022. We do the steering externally with a high resolution of the generator. Then we have 10 megahertz PPS splitter, 2 Septentrio Polarex 5TR receiver, an antenna on the top of the building, and a GNSS splitter. Here is one of the masers, the whole equipment, and the antenna on the top. Our self-imposed goal is to stay within plus minus 10 nanoseconds from UTC. As you can see here, there were some hiccups. One important lesson is something that was not ideal and that we have to deal with, and we try to improve. Being guests in another lab means we did not have control on who had access to the lab. Also, we had no control on the temperature steering and temperature control of the lab. You can see here, for example, it happened at the same time that the temperature control failed. And at the same time, we had guests in the lab, also some technicians coming in to install some fibers without giving us notice, probably touched some cables on the maser. Something similar happened here. Here there was this temperature, a failure of the temperature stability. So fortunately, we had no control on everything that was happening in the lab. Okay, the second goal was the construction of a robust precise timing facility as an alternative and an improvement to the current Galileo design. The current Galileo design in the two precise timing facilities is based on a master clock and active hydrogen maser. There is, of course, some backup. There are also two precise timing facilities for backup. However, sometimes hiccups, of course, occur, and it has happened 5 years ago that there was no Galileo system time for more than 5 days. So how do we want to improve on that to prevent accidents from happening? We want to move on from the master clock principle and create a composite clock. We also want to have more than one manufacturer for the same capabilities, for the same measurement instrument. We want to buy, if possible, from 2 or more suppliers so that we are able to compare them and give recommendations on the pros and cons of each. And this applies not only to the hardware, but also to the software. So, for example, this composite clock implementation, the moment it's been written in Python, but we also want to implement it in other programming languages, for example, C. And then we can see which one works best, which one is more efficient. And also, we want to have enough redundancy that we can replace our equipment, test new hardware or software anytime without affecting the operations. Here are a scheme of the robust precise timing facility. So starting from the left, we have 4 active hydrogen masers and 4 cesium clocks. We have 4 different measurement chains. So we compare the clocks with phase comparators against each other. Then we have in each chain a composite clock algorithm that creates the implicit ensemble mean. The composite clock is based on Kalman filters. Then we do the steering to UTC. Then there are cleanup oscillators here. There are sort of very intelligent switches. So if the signal in one chain fails, it can switch automatically to the signal coming from another chain without phase jumps. And here we have the signal distribution. Okay, so that was the roughly 10 square meters lab where we were hosted. As you can see below, it was quite tight. We always joke with our boss that he hired us because we were skinny people. So we had no place anymore for any more equipment. But we got a chance in summer last year, to move the RPTF to a brand new lab in yet another building. However, it was decided that UTC DLR should stay in Caen, because part of the equipment belonged to them. Also, they needed an active allergen laser for another project. However, they had construction works. So in the entire building, they decided to redo the entire air conditioning. So we had to store UTC DLR in a room. We lost the calibration. There was no temperature control, no vibration control. So we had, unfortunately, to put it on a break. Okay, here is the brand new lab for the PTF. So now we have 60 square meters, 3 times as much as before. Here we have the 4 measurement chains, plus some more capabilities. So there's also some servers, all the distribution units, the rack with the cesiums here. Here are 3 of the 4 masers. As I said, one is stayed in the other building. And what's not shown in the pictures, but it's going to come here, there are also some optical tables, some capabilities for including optical clocks in the future. So current work and future plans. So for the RPTF, there's still some work to be done on the lab infrastructure, on the temperature control especially. We're finishing the inter-rack cabling, and we will establish a fiber link to the maser that's left in KN, so that we can also have signals from the masers. Regarding the software, the first composite clock implementation works since a month, which is a very exciting result and opens the door for many future ideas, future implementations, capabilities. The plan now, well, it works in one chain. We have to extend it to the other chains, implement the fault detection capabilities, and an exciting goal is that we will incorporate optical clocks. Regarding the UTC, after some negotiation, we have decided eventually that the UTC will come back to us, so it will be in the same lab as the RPTF. We will do it with a different maser, different antenna cables, which means we need a calibration campaign later in the year. We have already asked PTB for this. More long-term goals. So we will have a fiber link to PTB, the Meteorology Institute of the National Meteorology Institute of Germany next year, so that we can steer to UTC PTB, which is very, very close to UTC. And we will have finally a new GK building in 2027 with even more lab space. So the entire basement will be dedicated to labs, and we will have 60 square meters just for the clocks. I was asked also to give some lessons, to give a quick, what kind of lessons we have learned. Being new to this, we learn something every day. It's never boring. But yeah, I put a few here. Say we are a very young team, so we all started in 2020, 2023. We have a new colleague that started 3 weeks ago. So we're very young, but it's very important to keep a good connection to the more experienced colleagues in the timing community. So we're both Johan has been in the timing community for 25 years, but also important to keep connected to all the rest, and you guys have been very, very welcoming, I have to say. Also, something new for me, I've always worked in teams of physicists, more or less all with the same background, and now I have an interdisciplinary team. So it takes maybe more time to get everyone on board on the same page, but then everyone can play on their own strengths. So, for example, I have a very good software engineer that does amazing things with data, saving data and visualizing and so on. Another thing I already mentioned, the infrastructure, very important, and control was access to the lab. So no matter how many signs, do not touch signs you put on the maser, someone will find a way to touch the maser. Also, what we've learned, good documentation really saves a lot of time. We document everything from the number of the cable, where it's going, where to which input of which instrument. That's really fundamental. And yes, really say data storage, notification in case something goes wrong, and also visualization tools. Very important, but empowering, allows you to have a good look at what's happening, and if there are some problems. So find yourself a very good software engineer that can do that for you. And that's the conclusion of my talk, and thank you for your attention.
Thank you very much for your presentation. One question, anyone? Please raise your hand. Patricia?
Yeah, I'm sorry. Thank you, Laura, for your presentation. Do you have any idea of when you will be ready to be back in UTC?
Well, I suppose after the calibration has taken place, we have asked to have it in autumn.
Okay, thank you.
Yeah.
Let's thank Laura again and move on to the next speaker. Our next speaker is from NPL UK. Helen Margolis is the head of science for the Time and Frequency Department at NPL, with overall technical responsibility for the National Timing Center program. Welcome, Helen.
Hello. Thanks, Marina, for the introduction. Can you see my screen? Okay.
Yes.
Yep. Okay. So yeah, sorry, went too fast. I'll start with just a little bit of motivation for why we've started up this program. So obviously it goes without saying for this audience, but time and frequency underpins so many of the technologies we depend on in our daily lives. But most users of accurate time and frequency signals, and that includes operators of critical national infrastructure, rely on timing signals from global navigation satellite systems, or GNSS. And that's because they're free and widely available, but they're also weak and vulnerable to natural, accidental and deliberate interference. And the UK's over-reliance on timing signals from GNSS has been highlighted in a number of reports over the past few years. So the London Economics Report, published in 2017, estimated that the economic impact to the UK of a disruption to GNSS would be £5.2 billion over a 5-day period, a lot. And they also said that 90% of the use cases they'd identified were down to timing rather than position or navigation. The Blackett Review in 2018 really reiterated how important GNSS had become to our daily lives, but it also emphasized another point that's really important, that our awareness of this dependence was out of step with the extent to which we depend on it. And so it was with that in mind that we established the National Timing Centre programme to start really to try and address this problem. So the work on an initial R&D programme started in 2019, although it wasn't actually announced by the UK government until February the following year. Then later that year, the over-reliance on navigation and timing services from GNSS was actually highlighted in the UK National Risk Register for the first time, actually within the risk associated with severe space weather. And it was really recommended that critical users ought to be exploring backup solutions, and they specifically mentioned engagement with the NTC programme in terms of resilient timing. So since then, I would say that the risks have actually become more severe. We've seen a rapidly increased dependency on digital infrastructure, partly as a consequence of the COVID pandemic. And GNSS jamming is also becoming an increasing problem, particularly when we look at the jamming we see around conflict zones. So actually in the UK, quite a high profile example recently was the jamming of an RAF plane carrying our UK Defence Secretary, Grant Shapps. There was no actual problem, but the caused by the jamming, but it was a high-profile incident. And then in the latest update to the National Risk Register last year, the loss of position, navigation and timing services was actually separated out into a standalone risk for the first time. And alongside that, we saw the creation of a new national office with responsibility for position, navigation and timing, which is working towards the implementation of a 10-point plan to address the risk. And that includes the next phase of the National Timing Centre programme. And I'll come back to that at the end, but for now I want to focus on the initial phase, the R&D programme. So that has three main objectives. The first is to design and implement a new, more resilient UK timescale, and that will be geographically distributed across several locations rather than being located at a single site. The second objective is to provide innovation opportunities for UK companies by providing access to accurate and traceable time and frequency signals, as well as to expertise and funding. And the third is to respond to a shortage of specialist skills in time and frequency by providing training material and opportunities. So today I want to focus on the first objective, which is the implementation of the new UK timescale. And we're calling this the Resilient Enhanced Timescale Infrastructure, or RETSI for short. So in due course, RETSI will become the source of UTC MPL, distributing traceable time and frequency signals to a wide range of potential end users, and those end users will include critical national infrastructure. So that's really a big deal. Critical national infrastructure will be depending on RETSI to mitigate the risks posed by their current over-reliance on timing signals from GNSS. So the resilience of the timescale will be really key. And by that, I mean the ability of the timescale to withstand, adapt to, and recover from challenges. So what that means is that we've had to think very, very carefully about a whole range of factors such as redundancy, real-time monitoring, physical security, and cyber security. And also because the point is to reduce the risk posed by over-reliance on GNSS, the operation of the timescale must not depend on GNSS. It has to continue to operate in the event of a GNSS outage. So RETSI is designed as a mesh of 4 linked timescale laboratories, and we're calling these core nodes. So these core nodes are separated geographically within the UK, and they will all be located at secure sites. And each of these core nodes contains atomic clocks and associated time and frequency distribution hardware that generate several different timescale realizations. So then at any given time, one of those timescale realizations at one of the core nodes will be identified as UTC MPL, and we call the associated site the primary site. Then we have the other timescale realizations at the primary site and the other core nodes, which are generating backups to UTC MPL. So this multi-site design and the geographic separation of the core nodes improves the resilience of the system because it protects against any challenges that are local to a given site. And of course, RETSI will be a UTC-K timescale, so it will also need to contribute data to the BIPM for the computation of TAI. And that data will always go via the primary site, which in the example I've shown here is core node number 2. So I've indicated that transfer to the BIPM by the thicker dotted line. But the core node that generates UTC MPL could be changed from time to time within the mesh. So the basic building block for the design of RETSI consists of a hydrogen maser and frequency offset generator, along with some associated distribution equipment that I've just left out of this diagram for clarity. So the unsteered clock outputs are the ones that we'll use for the data submission to the BIPM for TAI, where the steered clock outputs form the physical timescale realization, which here we're calling a UNR. And then both the unsteered clock signals and the steered clock signals are monitored using phase comparators and time interval counters. So then at each of the core nodes, we will have 4 of these UNRs or timescale realizations. Each of these will be produced using an independent hydrogen maser and frequency offset generator. And of course, these UNRs actually consist of a set of coherent frequencies. So we'll have 1 PPS, 10 megahertz and 100 megahertz signals here. Then at each core node, we'll choose one of the UNRs as the reference timescale realization for that site, which we then call UN Hub. And that's achieved using a timescale switch, which enables the UN Hub to be switched to an alternative UNR if necessary. And as you can see in this diagram, the timescale switch, as well as the distribution amplifiers for the UN Hub outputs, are duplicated in a separate hardware chain to avoid having what would otherwise be a single point of failure on the site. And then finally, one of the 4 UN hubs will be selected to be UTC MPL. But so there here, a unique feature of RETSI is that the UN hub defining UTC MPL can be changed to a different physical realization at a different site in a process that we've called site selection. So the core nodes are then connected to each other by a mesh of time and frequency transfer links, which enable the different UN hubs to be compared. The primary technique used is time and frequency transfer over optical fiber, because that enables us to carry out the comparisons with the lowest possible noise. But we'll also have 2-way satellite time and frequency transfer links between sites, and operating those 2 different modalities increases the resilience because they've got different failure modes. And also what's really important, given that RETSI is designed to mitigate the risk of over-reliance on GNSS, both these methods are independent of GNSS. We will also use GNSS time transfer methods to cross-check the measurements of the other time transfer links and for calibration of the link delays, but RETSI won't be operationally reliant on those links in the sense that a disruption of GNSS will not disrupt the output signals from the timescale. And then, of course, traceability of the output signals to UTC will be maintained via the international 2-way satellite time and frequency transfer links, along with calibrated GNSS measurements between UTC MPL at the primary site and other UTCK labs. So we'll implement a steering algorithm to keep all the timescale realizations aligned with each other within defined limits, as I've shown here, and also to keep UTC MPL within a defined offset from UTC. So the algorithm will have both a frequency lock part and a phase lock part. We'll have a stable reference frequency, which we generate from an ensemble of cesium fountain primary frequency standards operated at different core nodes. And the frequency lock part of the algorithm will steer every timescale realization independently using information from all cesium fountains available in the mesh, including any remotely located ones. And then the phase lock part will combine time offset measurements made in real time with cesium fountain data and post-processed data on the deviation from UTC as published in Circular T. And of course, cesium fountain data from RETSI will also be submitted to the BIPM, contributing to the evaluation and steering of the UTC scale interval. We'll be continuously assessing the status and performance of the system using monitoring software running on dedicated servers with key information available to operators via a monitoring dashboard. Then hardware and software performance metrics and logs will be monitored and will feed a hierarchy of alarms, warnings, and notifications to alert operators to any issues that might arise. And then the switching part is really key to our design, so at each core node, the UN hub can be used to switch between different UNRs. to change which one is designated as the reference UN hub for that site. That might be necessary, for example, if a component in the UN hub chain fails, or if the stability of the UN hub degrades, or if we need to carry out preventative maintenance on that particular chain. And then from time to time, it might also prove necessary to change the primary site, by which I mean selecting a different UN hub as UTC MPL. So this might be the case, for example, if the primary site is unresponsive for some reason, if links to the primary site from other sites have failed, if the international two-way links from the primary site to other NMIs have failed, or maybe if major site maintenance is planned. So in terms of the status of the new timescale, the design's been baselined, the implementation is underway. We're installing the equipment on a site-by-site basis. So the hardware testing and integration is well advanced at site 1, and lab refurbishment has also started at site 2. We've completed the first cesium fountain for RETSI, and optimization and a full uncertainty evaluation are now underway, and a second fountain is under construction. A large amount of software development is ongoing, and also we are currently evaluating potential locations for sites 3 and 4. As we complete each site, we'll form the time and frequency transfer links between the sites. And then eventually, as we complete a robust program of testing, we'll undertake the work that's necessary to transfer UTC MPL from our legacy infrastructure in Teddington across to the RETSI mesh. So then in terms of distribution to end users, this will be achieved via a tiered hierarchy of what we're calling user access nodes. But first of all, between RETSI and the first downstream user access node, we have what we're calling orchestration nodes. So these act as a kind of security buffer between RETSI and the users. So the nodes that connect directly to the orchestration nodes are called tier 1 user access nodes, and those are located at the 4 RETSI sites. And then from the tier 1 user access nodes, we can either distribute directly to end users or via further tiers of user access nodes, which are located beyond the RETSI sites. So the methods and protocols that we use for distribution might vary according to the needs of downstream users. They might be different for different user access nodes. And also the operational models for the user access nodes are likely to be different in different cases, because we can expect that, critical national infrastructure, industry and academia will all have different requirements and different expectations, for example, in terms of service level agreements. So a quick look at the orchestration node. So this provides 2 services to the tier 1 user access nodes. So the first is a timing signal service. So this gives 1 PPS and 10 megahertz signals, actually from both the co-located and the remote UN hubs, as well as 10 megahertz signals from all co-located free-running mazes, and also a time code. Then the second is a status signal service that indicates whether the distributed time and frequency signals are within specification, as well as providing information about pending leap seconds. And this status signal will be updated every minute. Then any additional signals or time dissemination protocols that are required by users will be generated in the tier 1 user access nodes. As an example, we'll include PTP equipment to operate our MPL time service to users in the financial sector. So then, just very briefly, I mentioned the UK framework for greater PNT resilience earlier. And the National Timing Centre is a key element of the 10-point plan, which has been drawn up by what's now the National PNT Office. And the people in that office are now hard at work on the business cases needed to justify the investment that they require to implement their plan. So the next phase of the work is planned to go beyond the completion of RETSI and its transition to an operational infrastructure. also starting work on distributing the signals to priority users across the UK, but also to address the resilience of the supply chain and starting to think about integrating optical clocks into RETSI in anticipation of a future redefinition of the second. So that's basically it. But just before I finish, I wanted to mention 2 e-learning courses that we've developed as part of the NTC R&D programme, which I thought some of you might find of interest. So they're both offered free of charge on the NPL training e-learning platform, and initial feedback actually has been very positive. So please do take a look at those if you're interested. So that's it from me. Thank you all for listening, and I'd be very happy to take any questions.
Thank you very much, Helen. Very interesting presentation. Questions, anyone? Please raise your hands. People are overwhelmed.
So am I.
Well, thank you again, Helen.
Okay. Thanks.
And we'll move to the next and last presenter for today. Ashish Agrawal has a PhD from JNU New Delhi University in nonlinear and quantum optics. He's been working at NPLI for the last 26 years on the projects that include rubidium vapor cells and clocks, cesium fountain, development of primary and secondary time scales. Ashish is leading time and frequency metrology at NPLI. And I welcome Dr. Ashish Agrawal. Please to share your screen.
Thank you for this time, and I'd like to thank the organizers for this opportunity. Let me share my screen. Just a sec, yeah. Share it from the other side.
You're not sharing yet. You need to click the share button, I think. Great.
So basically, I'm going to talk about the timing centers which we are developing in India. I'll talk about the telecom sector also, because we already heard that there is a requirement to move away from GNSS, and there is a requirement to have a resilience. So we are planning that in the country we need to cater to the requirements of telecom sector, the navigational systems which we are developing in India, the stock exchanges, the power sources, synchronization of that, and security and defense systems which we are also having. So I'll present to the audience the requirement of having time scales across the country, and what is the architecture which is being planned, what are the components of the time scales which we are having, and then also I'm going to present about the performance specifications of these time scales which we are planning, and how we are doing in our NAVIC, our own regional navigation system which we are having. So I'll talk about the physical requirements of civil, electrical, and networking for at all these sites. Firstly, let us talk about how is telecom sector dependent on the resilience which we are talking about. We are trying to move away from GPS, because all these all the cell towers, the base stations, and network elements and user devices need to be synchronized, and that requirement is within 30 nanoseconds. So we also require our own navigation system in India, and this is being run by ISRO, our space agency, and we are having accuracy requirement of about few nanoseconds for the navigation using NAVIC satellites. Then we have a high frequency trading stock exchanges in the country, which also I think across the world, and they have a very tight requirement of 0.3 microsecond or lower. So same with the power grid also, where we have PMUs in different grids, and they need to synchronize different generators, the relays, the phasor measurement units. And to maintain the grid stability, we require at least 1 microsecond of data analysis stability. So we have other requirements like digital economy, the digital signatures, where also we have a requirement of about 1 second to 100 millisecond. So these requirements are very stringent, and I think we need to really cater to all these sectors. The railways also require for train control and also for signaling systems. For onboard train systems, we require accuracy of about 1 millisecond. And we are also talking about weather stations, the sensors for monitoring various, remote sensing systems, LIDAR and all that also require accuracy of about microsecond or so. And we are now in the era of live matches and professional broadcasting, where stringent requirements is about 100 nanoseconds to 1 microsecond. We are also trying to cater to the cyber security using the timing resilience which we are having, and that also requires about accuracy about 10 milliseconds. We are all aware of the strategic requirement of timing, and in our defense systems, the missile guidance systems also require a highly accurate 1 microsecond accuracy. So how we are doing in India, we are already setting up 2 time scales in Bailalu and Lucknow, which is already working. And they are having a link to NPLI using NAVIC Common View and also GNSS Common View. And we are also doing the two-way between these stations and NPLI. So other than that, we are setting up 5 more stations across the country, and the cities are in north, east, west, north, south, and central of India. And basically the requirement is because we need to create a robust and reliable and resilient infrastructure for telecom sector, and also which will have lower latency for the users. And we'll also be able to prepare for the disaster as such. So we also need to scale this in future and move to newer time scales across the country. What we are trying to do is that we are setting up 4 atomic clocks at each of these sites, and these are passive hydrogen masers. And we are using at all these sites 2 time scales we are developing at each site, and that is what the resilience is all about. So we'll have a switch and a microphase stepper, and we'll also be having resilience in GNSS because we also have a NAVIC timing receiver inbuilt into the system. And finally, we'll be able to distribute time to various users using NTP and PTP from these sites. And we have a clear ensembling and steering algorithm which has been developed for these time scales. We are planning to have a disaster recovery also for the primary time scale at NPLI. And this disaster recovery will be at Bangalore. And this disaster recovery will consist of 3 active hydrogen masers. And we will like to then contribute using these active hydrogen masers to TAI also, if possible. So the major components which we are having at these time scales is active hydrogen maser, passive hydrogen maser, phase and frequency comparator, phase and frequency offset generator, the NAVIC and GNSS receiver, and the amplifiers, and also the high frequency switch. So I have basically, for the sake of audience, listed what we are planning to use, what all models we are planning to use. So these are just indicative that what we are planning to use right now in our time scales. So we also require minor components like servers, the network switches, the router, the NTP servers, the PTP servers, the firewall, the RKM, the KVM, the GSM modem, the serial to LAN converter to all these sites, along with the measurement equipment like oscilloscope, spectrum analyzer, phase noise emission test set, the multimeter, time interval counter, the PTP tester. So because all these are very, very essential to do the measurements of different kind and test and calibrate them when we are installing all these equipment. So of course, we are aware that we are having requirement of building the cables. So electronic workbench and racks are just trivial requirements. But finally, what is the infrastructure? Why we are creating this? Basically, 2 time scales at each site, primary and backup, which is automatic with the automatic changeover, no common elements other than atomic clocks. we will have sufficient redundancy at all these sites to avoid single point failure. And we'll have traceability to UTC NPLI via the NAVIC and the GNSS common view. And we'll also use the capability to build our own algorithms, ensembling and steering algorithms. We will be doing the remote and local monitoring of this time scales, and we'll have a control system developed for all this from NPLI. And we'll also doing the data acquisition and uploading to BIPM as and when required. And we also are working for the national critical information infrastructure. So we need to build a cyber secure network, and that is where we are putting an MPLS link. And we want to disseminate from these labs, these timescale labs, the NTP and PTP, so that all the users get direct traceability to NPLI. And all these sites will, of course, have a robust environmental control and power backup systems. The plan is that we will have frequency outputs at all these sites, 5 megahertz, 10 megahertz, 100 megahertz, and 1 PPS timing output, other than the IRIG-B and NTP and PTP protocols. So the accuracy at planned at each of these sites is about 30 nanoseconds of UTC NPLI, and frequency offset of about 5 10 to minus 13 average over a day. So basically, it will have a very good frequency stability and very low phase noise, and there'll be redundancy, as I said. Before PHMs will be installed to develop two time scales, redundant time scales. So the common elements will be these atomic clocks, and other than atomic clocks, there'll be no other common elements in these time scales actually. So that is what the plan is. The performance of NAVIC has been improving, and it is right now within plus minus 7.5 nanoseconds of UTC NPLI. And we are trying to continuously steer it using the two-way link which has been created between NPLI and these two sites. So we will like to talk about the physical requirements which are being talked about while setting up these labs. We do have raised false floor at all these sites. The lab partition for segregating the atomic clocks with other infrastructure is being planned. It has been implemented already. The false ceiling to bring the cold air and take away the hot air and all that is being also planned. So the insulation of the walls, because India is a hot country and we need to insulate from thermal environment. And we also are planning to have a robust UPS system, the AC plant, which is which is having also 1+1 redundancy. We will like to have a robust antenna structure, and I talked about here that how we are planning that we have a 5 by 8 inch threaded mount, which we are planning to directly put on the thread at the top of the roof. So we are planning to have also vibration-free platforms for the. We have already put the active hydrogen measures on the vibration-free platform at all these at our DRC site, and we are also trying to develop the electrical parameters, like all the data logger for the monitoring the temperature and humidity at all these sites. We plan to have genset and the UPS as a AC power backup. For 24-volt DC power, we have put this on wall, this XLR and plus minus 24-volt DC supply boards, so that all the equipment is on multiple redundant power as such. And we are also planning to install lightning arrestor, and it has been already installed actually. And then we will have a biometric access to these labs. The CCTV cameras are being installed, and the fire alarms and the MPLS link to the network, and the Cat6 cables are being installed at all these places. So this is a typical MPLS connectivity between different sites. I told you about 5 sites. So these 5 sites are in 5 corners of India, and these are all connected using MPLS dedicated links from the government. And they are also having redundancy in ISP. 2 ISPs have been chosen so that we have a foolproof network between the sites. And we also plan to now disseminate from these sites using NTP and PTP a Actually, from NPLI, we are planning to also have a fiber link to dark fiber link to a nearest site, which is only 70 kilometers away. And we are already trying to do a time transfer between this site. So we are using both the techniques of PTP and White Rabbit as a proof of concept for doing time transfer about a site which is 70 kilometers away. So this is the plan of India, because we are also trying to assess that GNSS is very vulnerable, and we should have a resilience, and we should depend on the national timing infrastructure. So as was talked about by Helen also, we are very much geared up to create these timing centers across the country, and we call them secondary timing laboratories. And we also are bringing in disaster recovery in Bangalore. So with that, I thank you all. I thank my team also at NPLI for all this hard work. Thank you very much, everyone.
Thank you very much, Ashish, for this presentation. Thank you all very much, and hope to see you again at the next technical exchange. Thank you.